right, this is Unit 2, Lesson 3, Continuity. So the first thing that we want to talk about is what continuity actually is, and we have continuity at a point. So when we plot values of a function, usually we've been given that sort of data. So when we plot those functions and when we draw a line from one point to another, we are assuming that it's a continuous function. We're assuming that we're graphing basically things that we don't actually know about. But if that line is continuous, it is considered a continuous function. So we're assuming that it's continuous. We've assumed that it's been continuous since we were probably in 3rd, 4th grade when we started graphing lines. And up to like 7th grade, we're still graphing lines. We're always connecting points. We're always told that we need to connect the points and the lines continue versus a line segment, okay? So any function y equals f of x whose graph can be sketched, and you can basically start your pencil at one end and continue in one continuous motion without that pencil being lifted is a continuous function. So continuous functions are functions we use to find a planet's closest point as it approaches the sun, or the peak concentration of antibodies in blood plasma, all sorts of different things we use continuous functions for. Okay, so they are also the functions we use to describe how a body moves through space or how the speed of a chemical reaction changes with time. So in fact, most physical processes, so anything that you learn really about in physics, has a continuous function that you are graphing, okay? So you can continue graphing it over time, and you can look at any one of those specific points and you can find data to match that actual point. Okay. So as a result of discoveries and things like that, and that because of the heaviest use of discontinuous functions in computer science, statistics, and mathematical modeling, the idea of continuity has become one of practical as well as theoretical importance. So just like you can have a continuous function, you can also have a discontinuous function. And so in order to understand what continuity looks like, we need to look at the function. So from the limit that we investigated last lesson, or in the first lesson, first lesson, so example 8, section 2.1, which we can look at, we need to see how they kind of work. So if we're investigating continuity, I want to find the points at which the function f in figure 2.18 right here is continuous, and at the points where it is discontinuous. So the function f is continuous at every point in its domain from 0 to 4. So anywhere I go here, it has a point, so it's continuous, okay? Except where x equals 1. Because there's an open circle there. So at those points, there are breaks in the graph. We can note the relationship between the limit and the value of f at each point of the function's domain. So at points at which f is continuous, so x is 0, it's continuous. So there's 1 that way. The limit as x approaches from the right, f of x equals f of 0. At x equals 4, we can look at the limit as x approaches 4 from the left. Coming from the left, it appears it goes to 4. F goes to 4. At 0 is less than c is less than 4, where c does not equal 1 or 2. The limit of f of x as x approaches c equals f of c. Okay. However, there are points on this graph where it is. So at x equals 1, so x equals 1, the limit f of x does not exist. So as I approach from the right, it does exist. And as I approach it from the left, there's this discontinuous function here. At x equals 2, the limit of f of x as x approaches 2 equals 1, but 1 does not equal f of 2. Again, there is this So f of 2 up here, this closed dot, but I have an open dot here. So this does not equals this, so it's discontinuous there. At c is less than 0, so anything less than 0 we don't have. And at c is greater than 4, we also don't have, so it's discontinuous because they're not points in that domain. So to define continuity at a point in a function's domain, we need to define the continuity at an interior point, so a point that's inside, and continuity at an endpoint, so the two at a left endpoint and a right endpoint. Okay. So we can see here that as we approach continuity from the left, here's an endpoint B, and continuity from the right, endpoint A. And then two-sided continuity is point C, so some point in the middle. So interior point, a function y equals f of x is continuous at an interior point C if its domain if the limit of f of x as x approaches C equals fc. Okay. So as I approach that point, if that's that point, it is continuous on the interior. A function y equals f of x is continuous at a left endpoint, A, or is continuous at a right endpoint, B, if its domain, if the limit of f of x as x approaches A from the right equals f of A, or the limit of f of x as x approaches B from the left equals f of B, respectively. So if a function f is not continuous at a point C, we say that f is discontinuous at C, and C is a point of discontinuity of f, but that C doesn't need to be a domain of f. So I want to find, for example, the points of continuity and discontinuity. So I want to find the points of continuity and the points of discontinuity of the greatest integer function, which is in figure 2.2 or 2.20. So for the function to be continuous at x equals c, the limit as x approaches c must exist first and must equal the value of the function at x equals c. So the greatest integer function is discontinuous at every integer. So for example, as the limit of integer x, as x approaches 3 from the left equals 2, and the limit of the integer x as x approaches 3 from the right equals 3. So they're not the same. So the limit as x approaches 3 does not exist. So we notice that the integer 3 equals 3. In general, if n is any integer, the limit integer x as x approaches n to the left equals n minus 1, and the limit of integer x as x approaches n from the right is n. So the limit as x approaches n does not exist. So you can look at this because this is a step function, okay? So I can see as I approach any of these from the right and then from the left, I get two different answers, so they don't exist. Okay? So the greatest integer function is continuous at every other real number. So for example, the limit of integer x as x approaches 1.5. So 1.5 is right here. Okay. As I approach from the left, I get 1.5, and as I approach from the right, I get 1.5. So 1.5 again is right here in the center. Okay, so I'm looking right here. Okay, so as I approach from the left, as I approach from the right, they equal the same thing. That's what this means. Okay. So in general, if n minus 1 is less than c is less than n is an integer then, limit of integer x as x approaches c equals n minus 1, which equals the integer c. Okay, so basically I can take any of these points. So I can do 2.5, 3.5, 4.5, I could do 0.5, I could do negative 0.5, I could do negative 1.5. They're all going to be continuous at those points. So they're not discontinuous at their endpoints, but they are continuous on the interior points. So figure 2.21 is a catalog of discontinuity types. So the function in A is continuous at x equals 0. So here it's continuous at x equals 0. The function in B would be continuous if it had f of 0 equals 1. So again, there's this open dot. There's a closed dot, so it just continues on through. Remember, the closed dot means it's equal, it's greater than, less than, or equal to. It includes all of those points. The open dot doesn't include that specific point. So it's continuous going this way and this way, but it's discontinuous at that point. The function in C would be continuous if f of 0 were 1 instead of 2. So again, I have a point up here and this discontinuous point here. In the discontinuities in B and C are removable. So each function has a limit as x approaches 0, and we can remove the discontinuity by setting f of 0 equal to this limit. The discontinuities in D through F are more serious. So for D, the limit as x approaches, the limit of f of x as x approaches 0 does not exist, and there's no way to improve the situation by changing f at 0. So I can see that right here, there's this big jump. The step function in D has jump discontinuity. So it jumps. It goes from here to here. It jumped. Okay? The one-sided limit exists but have different values. The function f of x equals 1 over x squared in E, okay, has an infinite discontinuity. So I can see that they will never touch here. So remember, we talked about vertical and horizontal asymptotes. So because they have vertical and horizontal asymptotes right here, and then right here, in this case along the x-axis and the y-axis, so when x equals 0 and y equals 0, there's an infinite discontinuity. You'll never go past that line. We can't fix it, okay? And then there's this crazy function over here, y equals sine of 1 divided by x. Okay, that has oscillating discontinuity. So anytime, if I were to look at this function and I were to scroll in closer and closer, you would see this craziness going on, okay? But it oscillates and has no limit at x as x approaches 0. Okay, because again, you can't divide by 0. So there's this. So this one is oscillating. So oscillating discontinuity. So basically, if you have this really cool wave function and then it just breaks at a certain point, that's oscillating discontinuity. So anytime it actually breaks, there's something that's discontinuous about that function. So you can remove discontinuity. Okay, so you can actually do that where you set the limit equal to whatever that discontinuity is. So in like A, well, really in B and C, there are ways around it. Okay. So the function G is a continuous extension of the original function f to include x equals 3. So originally, when I solve this, if I factor the denominator, the domain, I can't have any x equal to 3, or it will be 0. Okay, so there has to be some sort of discontinuity in this equation because I can set x equal to something and make my denominator 0. So what I can do, I can show that x minus 3 is a factor of the numerator of f and remove all common factors. Then I can compute the limit as x approaches 3 of the reduced form for f. And then I can extend the function. So x of 3 minus 7x minus 6 over x squared minus 9, where x does not equal 3, and then 10 thirds at x equals 3. So it's continuous at x equals 3. The function g is a continuous extension of the original function f to include x equals 3. So continuous functions, a function is continuous on an interval if and only if it's continuous at every point of the interval. So a continuous function is one that is continuous at every point in its domain. So at no point in time, there's no jumps, there's no oscillating discontinuity, there's no infinite discontinuity. It has a value at every point. So y equals x is a continuous function. Okay. A continuous function need not be continuous on every interval. So for example, y equals 1 over x is not continuous on -1 to 1. Okay. It's continuous everywhere else. So example 3, identifying continuous functions. The reciprocal function y equals 1 over x is a continuous function because it is continuous at every point of its domain. However, it has a point of discontinuity at x equals 0 because it's not defined there. Okay, so at x equals 0, that's the point of discontinuity. So this is still a continuous function, but it has a point of discontinuity. Okay. Polynomial functions f are continuous at every real number c because the limit of f of x as x approaches c equals f of c. Rational functions are continuous at every point of their domains. They have points of discontinuity at the zeros of their denominators. So for example, 1 over x has a discontinuity point of x equals 0 because I can't divide by x, the 0 of the denominator. The absolute value function, y equals the absolute value of x, is continuous at every real number. The exponential functions, logarithmic functions, trigonometric functions, and radical functions are continuous at every point of their domains, and all of these functions, so all of those functions are continuous functions. So polynomial functions, rational functions, exponential, logarithmic, trigonometric, absolute value functions, all of them are functions. Some may have discontinuity points, but they're all continuous functions. Algebraic combinations. So as you might have guessed, algebraic combinations of continuous functions are continuous wherever they are defined. So basically, if I have two continuous functions, I can add them together, I can subtract them, I can multiply them. I can multiply them by a constant, or I can divide them, provided, of course, that g does not equal 0. G of c does not equal 0. Okay. I can also do composite functions. So all composites of continuous functions are continuous. So that means the composites like y equals sine x squared and y equals the absolute value of cosine x are continuous at every point at which they are defined. So the idea is that if f of x is continuous at x equals c and g of x is continuous at x equals f of c, then g of f is continuous at x equals c. So if we look at figure 2.3, so I have one of my functions is continuous at c, one of my functions is continuous at f of c, so g of f is continuous for both functions. Okay, so in this case, the limit as x approaches c is g f of c. So as x approaches c is g f of c. Okay. So composites of continuous functions. If f is continuous at c and g is continuous at f of c, then the composite g of f is continuous at c. Okay. So if f is continuous, g is continuous, then the composite is continuous at that specific point. So using theorem 7, the composite of continuous functions theorem, I need to show that y equals the absolute value of x sine of x over x squared plus 2 is continuous. So here's the thing. This is going to be a continuous function. Okay. So it suggests that the function's continuous at every value of x because g of x equals the absolute value of x is a continuous function at all its domains, and f of x, x sine of x over x squared plus 2 is also a continuous function. Okay, so there's no value here that I can put in to make this equal to 0. the bottom equal to 0, so it's a continuous function. We know that the absolute value function g is continuous and the function f is continuous by theorem 6 here. So their composite is continuous by theorem 7. And that's actually what it looks like. Looks like a really pretty graph, actually. So this function's continuous, this function's continuous. When I smoosh them together, they are continuous as well. So the intermediate value theorem for continuous functions. So functions that are continuous on intervals have properties that make them particularly useful in math and in its applications. So one of these is the intermediate value property. So a function is said to have the intermediate value property if it never takes on two values without taking on all the values in between. So again, it's continuous. So if I draw a line from A to B, okay, that means it continues, it has all of those properties as well from A to B. Okay. So theorem 8, the intermediate value theorem for continuous functions. A function y equals f of x that is continuous on a closed interval from A to B, so here's A to B, takes on every value between f of A and f of B. So in other words, if y naught is between f of A and f of B, then y naught equals f of C for some C in A to B. Okay. So basically I can pick any point in this function. They picked this point right here. That means that that value of y equates to some value on the x. Okay. So the continuity of f on the interval is essential to theorem 8. So if f is discontinuous at even one point in this interval, the theorem's conclusion could fail. So from here, it fails because there is this discontinuous point. There's a jump discontinuity. So a consequence for graphing connectivity, theorem 8 is the reason why the graph of a function continuous on an interval cannot have any breaks. Okay. So the graph will be connected, a single unbroken curve or line, like the graph of sine of x. It will not have jumps like those in a graph of the greatest integer function, integer x, or separate branches like we see in the graph of y over x. Okay, so it's a connected. Most people that graph can plot points. Some can turn on pixels between plotted points to suggest an unbroken curve. And for functions, the connected format basically assumes that outputs vary continuously with inputs and do not jump from one value to another without taking on all values in between. Okay. So basically when I'm looking at this function right here, x cubed minus x minus 1, this is a continuous function. Okay. So I could plot individual points and I could connect them loosely, but I don't necessarily want to plot every single one of these points on the graph. So I make connections in my brain knowing that this is how the graph should look. Okay. So example 5 using theorem 8, which is the intermediate value theorem for continuous functions. Is any real number exactly 1 less than its cube? Okay, so we can answer this question by applying the intermediate value theorem in the following way. So any such number must satisfy the equation x equals x cubed minus 1, or equivalently x cubed minus x minus 1 equals 0. So therefore, we're looking for a 0 value of the continuous function f of x equals x cubed minus x minus 1. The function changes signs between 1 and 2, so there must be a point C between 1 and 2 where f of c equals 0. And that is the end of lesson 3.